Welcome everybody to yet another of our weekly Bootstrap seminars. So today we're very happy to have Henry Maxfield tell us about JT gravity with defects and three-dimensional gravity. Thank you, Henry. Let's start.
Great. Yeah, so thanks for the introduction, Leonardo. So I'm going to talk mostly about this paper that appeared a couple of weeks ago in collaboration with Joaquin Turiachi. So I spoke about some of these things at Strings a couple of weeks ago as well. Since this is a Bootstrap seminar, there's also some sort of work in progress that relates this to modular Bootstrap in 2D CFTs. So that bit is still somewhat under construction, but I thought this would be a great opportunity to sort of tell you where we are and solicit a bit of feedback. And it'd be great to get your input on that aspect of it. So I'll have a little bit more focus on that as well. So at least the piece of this to do with JT gravity is very closely related to a paper that came out in the same week by Witten. So you should also have a look at that for a slightly different perspective. So the first thing to do is highlight my fantastic collaborator, Joaquin, on this work. So most of this would not be out in the world were it not for his input and hard work. So make sure he gets the credit due. Good. So the sort of outline of the talk is to begin with based on the gravitational path integral, which is, I think, a lesson for me from the last couple of years is that just the semi-classical theory of gravity, like an integral over metrics, without any strings or UV ingredients and so forth, seems to be a lot more, seems to know a lot more than perhaps it had any right to, or maybe we would have expected. So there are two simple theories of gravity that I'm going to focus on for the purpose of this talk. So the first is 3D pure gravity, and this in this case there's a natural way to try and construct the partition function of the theory to know what the spectrum looks like, and this is due to Maloney and Witten, and later refined by Keller and Maloney, and it's a very natural way to do that. So in this case, you want to do the path integral with some torus boundary conditions. So to compute that partition function, an actual thing to do is look for all the classical solutions with the correct boundary conditions. Once you have all the classical solutions, and in this case they can be completely classified, you compute all the loop corrections on top of that. And in that case, again, in this case, you can do that exactly, and then you add them all up. This is a very natural thing to do, and this builds your partition function. But what you get from this is problematic. It doesn't make sense as a quantum mechanical theory, and the sort of biggest problem with it, the sharpest problem, was actually pointed out not in the original papers, but much more recently by Nathan Benjamin and friends, who pointed out that if you look at very close to the threshold for a near extremal BTZ black hole, the density of states you get is actually negative, which is obviously a problem. There's been various suggestions on how you should cure this, but all of them so far involve modifying the dynamics of the theory, introducing some new matter, essentially. So the first aim of what I want to say is propose how you should actually modify or rather include extra contributions to the path integral just within pure 3D gravity, and those contributions that were there without modifying the dynamics actually cure this problem. Or at least there's a proposal for how they should do that. So that piece of the story turns out to be extremely close related to a two-dimensional theory of gravity. And while this first 3D pure gravity at first sight seems a little pessimistic, like it might not make sense, in 2D gravity, we've got beautiful recent results of Sadchenko and Stanford that computed the path integral here exactly. And the very important ingredient that's going to be a lesson for 3D gravity is that this path integral includes topologies where there's no classical solution. So they're not doing, so the Maloney-Winton strategy was to look for all the classical solutions and then look at loop corrections to those. But that strategy would not work for the Sadchenko-Stanford result. And we're going to sort of import that lesson into 3D gravity. The other somewhat, which okay, for us is going to be slightly less important here, but it's perhaps more wide-reaching in its consequences in general, is that this had a new sort of ADS-CFT duality, where the dual CFT, which is here just some quantum mechanics, is not a single, does not have a single Hamiltonian, but rather it has a random Hamiltonian, and we're actually going to find the 2D theory we're led to consider is actually generalization of this idea. And because this is the Bootstrap seminar, one of the arguments given for this negativity was something rather general, involving just modular invariance. And that argument was suggestive, but not completely. So the argument was made that there needs to be you need some matter, which means some states in the theory that have dimensions that would not be compatible with black holes. But that argument wasn't completely rigorous. There was a sort of little loophole, and the third aim of what I want to do is to explain where that loophole is and why this proposal is actually consistent with the modular bootstrap. And there'll be some sort of interesting universal results in the for spectrums of 2D CFTs that we get to along the way. So the first two bits, I'll try to go through relatively speedily, and if people want a few more details, then they're in the paper, or the strings talk is online, and then we can try and spend lots of time on this third part. And while I'm doing that, I'd like to invite any questions, interruptions at any point. The more interactive this is, the better. Okay, so very briefly, let's start with pure 3D gravity, unless there are any questions at this point. Okay, good. So the regime we want to study 3D gravity here is the regime where this negative density of states was pointed out. And that's for very near extremal black holes. And when we're talking about near extremal black holes, we can actually capture most of the physics with a two-dimensional reduction. So go about this in a relatively standard way that's indicative of a sort of general pattern in general dimensions. We start with just ordinary Einstein-Hilbert with negative cosmological constant, and through a sequence of steps, we arrive at JT gravity. So this first term is the Einstein-Hilbert action in 2 dimensions, but that's topological. It's proportional to the Euler characteristic chi with some coefficient, which I'll call S0. And then this second piece, oops. Then there's a second piece, and this is the Jakiv-Teitelboim gravity action. And this is, you need to include this to have some non-trivial dynamics in the theory. Otherwise, you're just describing sort of ground states. And this is this really does give you a good description of the physics. And you can, again, since this is the Bootstrap seminar, I'll mention that there's a Bootstrap argument that applies for very general 2-dimensional CFTs. It applies at large central charge, but you don't need any assumption of gaps or anything like that. You only need, okay, you need a non-zero twist gap, but you don't need to have a sort of what's it called, sparse spectrum or any of these sort of assumptions. And you can show that there's the physics of this 2-dimensional theory is really capturing something universal in any CFT2. This was described in this paper along with Anami Ghosh a few months ago. Okay, so we're led to study this from a 2-dimensional point of view. So let's see where this negative density of states comes from this perspective. So what we want to compute is a partition function. So we have some torus on the boundary. This is providing our boundary conditions. And the 3D geometries we need involve choosing a cycle to fill in and making a solid torus. So here is, so if you fill in this cycle, the spatial cycle, you get the empty ADS3. This just gives you the vacuum state, so this isn't that interesting for us. If you fill in the thermal circle, of course, you get a Euclidean black hole. And the density of states for the Euclidean black hole has some, first of all, exponentially large piece, which is the Bekenstein-Hawking entropy. It's given by the area of the BTZ horizon. And then if you go very near the threshold for that, where you get a near extremal rotating black hole, you get this square root edge. And this E equals J will correspond to the classical extremal black hole, and the density of states goes to 0, like with this characteristic square root behavior. Okay, so this is fine, but now we need to include another term. First of all, from the two-dimensional point of view, if we reduce on this spatial circle to get a two-dimensional theory, what we end up with is just the hyperbolic disk, and so we're just describing ADS2 with some circle fiber over it. And we can describe this with JT gravity, and this gives us a good, a parametrically good approximation of all the physics in this BTZ black hole. Okay, but the problem comes when we include some other saddle points, or the potential problem. And these saddle points are so-called SL2Z family of black holes, where you fill in some other cycle, which is a combination of spatial and time cycles. So in this case, I think we're filling in a cycle that goes once around the spatial circle and twice around the Euclidean time circle. Is the important saddle point for us. And it turns out that this gives a density of states that has some sort of Cardi-like growth, but with half the coefficient. So there's a much smaller number of states, half the entropy. It comes with this -1 to the power of the spin. So it's in particular, it's negative when you have odd spin black holes. But it has this different edge. And this is going to be the important piece, because while this goes to 0 as you approach the threshold, this is blowing up. So if you go to very, very low temperatures, exponentially low temperatures, or exponentially small energies close to the edge, then this second term can potentially dominate over the first term. And that's where the negative density of states arises, for this exponentially low energy above the threshold. Okay, so let's see where this comes from the two-dimensional point of view. When you do this reduction, because you're going twice around the time circle, when you dimensionally reduce over the spatial circle, you actually end up with a conical defect with defect angle pi here. And there's a Kaluza-Klein gauge field when you do this reduction, and this also has non-trivial holonomy around this point. So there's something singular going on from a two-dimensional point of view. But the three-dimensional geometry we started with is actually completely smooth. So this suggests that the two-dimensional theory, if we want to describe these things, we need to include some extra dynamical ingredients that describe this sort of behavior. So we should include these sort of defects in the Jakiv tidal volume gravity theory that's describing the near horizon behavior of black holes. So we'll, yeah.
Henry, can I ask a question? So presumably this dominates at a point where it dominates over the first term at a point where it's reliable. Is that true?
Let's see. Well, so in this case, you can compute all the loop corrections exactly. So it's one loop exact. So it's not. So it's in a regime where it's highly quantum. So there's this the Schwarzian mode is strongly coupled in this regime, and but for example, it's one way of saying it. But you can just solve the thing exactly. So at least perturbatively, there's no.
I see. So in this theory, it's the right answer. But if say you had 3D gravity coupled to some matter sector that you didn't know much about, would this term still be there in some sense, or it just that puts this term into a regime that you have no control over?
The term is still there in some sense, but there's potentially a load of other plus ... dots that you don't have any control over, whether they're larger or smaller. So yeah, this would probably be swamped by matter. Let's see.
Right.
So later when we come to the Bootstrap, we'll see a very precise sense in which this term is there. So it certainly, it's contributing something. Yeah, but there are potentially other corrections that could.
But this would be like arise at the same order as an instanton effect. So in any scenario where you had loop effects that were at all relevant, just this would not be an important contribution, right?
So maybe I'll
or you can
from the there's in the when we go to the Bootstrap piece, if you look at this density of states, or the density of primary states, and you take the include a factor of -1 to the j, so you're looking at the density of even spin states minus the density of odd spin states, and then you smear over some window, then it turns out that this is giving you this piece. So that would cancel everything out here, because all the odd spins and even spins completely cancel in the first term to very high accuracy, and you're left with this second term. And this really does give you the leading approximation to that density of even minus density of odd spins.
No, but
that's true in even with matter and so forth. So it's definitely.
You're saying that there's no possible loop effect that could arise when you add matter that would contribute to the difference of even and odd spins at high temperature?
There will be loop effects, but they'll come with a smaller. They'll grow small.
Why would they be non-perturbatively small? I guess it's just not obvious to me that
Yeah. So the point is there'll be loop corrections to this first term, but all those loop corrections are the same for even spins or odd spins. If you want to see a difference between, if you want to differentiate between odd spins and even spins, then this is the most important topology that is going to contribute. And
you're saying that no perturbative correction around the BTZ black hole could ever distinguish between even and odd spins.
Alex, the way you can see this from this CFT is that this second term Henry has is from the ST squared S image of the vacuum, and that's going to be the most important term when you take that. If you take tau equals to 1/2 plus I epsilon and take the ST squared image. Yeah. In that image, the vacuum dominates.
No, but
yeah, we'll see why this is true from the Bootstrap point of view. But yeah, what Nathan said is
just saying, right. Like just from the one loop determinant, or just from you're saying that there's no possible perturbative effect that could.
Yeah,
I can't even see that it's an integer, so that's
I guess that seems right. I'm just worried about if you had fermions or something like that. But anyway, I don't want to distract you because that's not okay. That's fine.
More interruptions are good.
Yeah.
Any other questions on this piece? This is almost all I'm going to say about 3D gravity. So
one little question. So if you want to compute the difference between, this difference between odd and even spins, you could just put the chemical potential, right? You could choose a tau parameter, so that with the complexified chemical potential of I pi, then that would automatically compute for you this sum, right?
Yes. So that is in essence what this. Yeah.
Okay. That's how they did it.
Yeah. Okay. So essentially, this SL2D saddle point is the thing that dominates when you take a large black hole, or so this particular limit of large near extremal black holes with an I pi chemical potential.
Yeah. So in that case, the BTC, the usual BTC, is probably subleading with that chemical potential. That might answer Alex's question.
Okay, yeah, so the last comment on this is something that's familiar in higher dimensions, where you something singular that arises from dimensional reduction. So it's like a Klein monopole that that you have some that look like the pole in 4 dimensions, but it's just a solution to pure Einstein gravity in 5 dimensions that's totally smooth and free of singularities, and it only looks singular from this 4-dimensional point of view. So this is something analogous. So we call this a Kaluza-Klein instanton, which is a very natural name. But from the JT point of view, we're now motivated to study something more general where you include any sort of detail. We're not going to worry too much about its origins. In this case, it's from this dimensional reduction from 3D, and it has this very special defect angle. But here we're just going to generalize this and study it with a general defect angle and a general sort of amplitude. Okay, so this is the next piece. I'll go through this fairly swiftly to get to the sort of Bootstrap perspective later. So let's start off with a review of JT gravity as solved by Saidshankar and Stanford, and we're going to then lean heavily on their strategy and just augment it with these new defect degrees of freedom. So here is the JT action, which is the same thing we wrote down before, except with now I've included this boundary term. I also need to tell you what the boundary conditions are. So here we have 2-dimensional metrics which have some 1-dimensional boundaries. So there's intrinsic data on the boundaries, which is just the proper length, which I'm going to take to be very large. So they're going to be living at some ADS asymptotics. There's also a dilaton, which I'm also going to take to be large. I'm going to hold their ratio fixed, and this is going to be the temperature of the dual CFT, if you like. So this is standard ADS CFT dictionary adapted to this particular 2-dimensional situation. And just for notation, what we're going to be computing is the path integral over metrics and dilatons with this action, but we're going to include any number of these asymptotic boundary circles. And this beta we'll call the renormalized length, and they're going to have n asymptotic circles, and compute the path integral over all geometries with those boundary conditions, and we'll denote it by this thing on the left-hand side, which, okay. And this eventually, this notation is because these z of betas will be interpreted as the partition functions of a dual quantum mechanics, but with a random Hamiltonian, and these angle brackets denote the average over that random Hamiltonian. So this is, for now, this is just notation, and that interpretation comes later. So as is sort of well known now, it's been a very popular subject of study in the last few years. This theory is completely solvable, and the important thing for us is that phi, this dilaton, appears linearly in the action. So it's just a Lagrange multiplier, and enforces the constant curvature condition on the metric. So that means the metric is completely rigid, because that determines the local metric to just be the hyperbolic disk, and there's only going to be some global data that defines it. And the only perturbative corrections that come here are from this boundary. And the important thing is that while the metric is going to be that of the Poincare disk, the location of this boundary, the physical boundary where we're imposing our boundary conditions, is not uniquely determined, and it can have this sort of wiggle, and integrating over these wiggles becomes this Schwarzian theory that people now know and love. And that gives you, in this instance, taking the topology of the topology to be the disk, you get this partition function from integrating over these wiggles on the disk. And there's this density of states. The thing to note here is that there's this e to the power of S naught piece, which is we can think of as like this as the Bekenstein-Hawking entropy. So it's like the Cardi entropy that we had in the prefactor for 3D gravity. And then when you go to very low energies, you get this square root of energy edge. Okay. So now we want to include other topologies in the path integral. And now there's some finite dimensional space of topologies. Once we've fixed these boundaries where we're always going to have these wiggles that we need to integrate over, the Schwarzian mode, there's some finite dimensional space of hyperbolic metrics. So the path integral, this infinite dimensional complicated integral, reduces to just this finite dimensional integral over the moduli space of hyperbolic surfaces with some particular volume, and the appropriate volume form turns out to be this Weber-Petersen measure. Okay, so once we've got that, we can write these amplitudes, that is the path integral with n boundaries. We'll focus on the connected piece of that path integral in terms of a genus expansion. So this is just the sum over topologies. It's the connected topologies with n boundaries in 2 dimensions are just classified by their genus. So these ZGNs are going to be the partition functions at fixed topology. And this prefactor comes from this Euler characteristic term in the action. Good. And the strategy for computing these path integrals at fixed topology is to cut things in two, or rather to cut off the boundaries and deal with those separately. And then we have 2 pieces. So one piece comes from the boundaries. So we're always going to cut along some geodesic that's homotopic to each asymptotically ADS boundary. There's always, this is guaranteed to exist. We can cut along it. It's got some proper length, which we'll call B. The integral over the outside is given by some version of the Shortian theory you already saw, which I'll call Z trumpet. And then we have this finite dimensional integral over the stuff that's going on inside this geodesic. And this is just a volume of this moduli space of hyperbolic surfaces. So it's given by these Weber-Petersen volumes. And then we just have to glue these things together. So the general formula is that we have these Weber-Petersen volumes that give us the stuff inside the geodesics. We have these trumpets that give us the wiggles of the asymptotic boundary. And then we just have to integrate over the lengths of this gluing geodesic. And that's how we construct all these amplitudes. Okay. So this is only as useful as these volumes. So we need to know what these volumes are. But fortunately, a great deal is known about these that we can extract from the literature. So Mirzakhani discovered or showed that these things obey a recursion relation. This is going to be the key tool in understanding this sum over topologies. And Einard Norentin pointed out that this recursion relation of Mirzakhani is very closely related to so-called topological recursion that's obeyed by matrix integrals. So now I have to tell you what a matrix integral is. Let's see. Yeah, so a matrix integral gives you amplitudes computed by some random matrix weighted by a particular special sort of kernel, which goes like, which has some potential, and what we're computing is correlation functions of partition functions, that is trace e to the minus beta h. You can have several of these. We have this weighting over different matrices, and we do this integral and we get these amplitudes. And from Tufts double line counting, these things have a genus expansion, which the topology of the surface on which you can draw Feynman diagrams gives you an expansion. So S0 here is essentially the L, which is the rank of the matrix. So H is an L by L matrix. And we don't really need to know what the topological recursion is, but it's a particular structure that determines all of these higher genus amplitudes uniquely in terms of a couple of starting points. So in particular, the genus 0, 1 boundary amplitude. That is the disk. So once you have the disk, you use this, you turn the handle and you get everything else. And the same is true for these Weber-Petersen volumes. There's a particular input, and then there's a recursion relation that you turn the crank, and that spits out all the volumes for any genus and any number of boundaries. And putting these things together, you learn that there's this duality between a matrix integral and JT. So we have this matrix integral is describing the path integral of JT gravity with n insertions of the partition function. You have these n boundaries in 2-dimensional gravity. The seed for this, the thing that defines this matrix integral, if you like, is this, the genus 0, 1 boundary amplitude, the disk amplitude, and that is this disk path integral we've already computed using the short-in theory. Then to get all the other amplitudes, you just apply this topological recursion, and the Mirzakhani's recursion is the thing that's playing that role in JT. And this correspondence works exactly to all orders in this genus expansion for any number of boundaries. So that says that at least order by order in the genus expansion, there's a matrix integral, and the matrix H that appears here, we can interpret as a Hamiltonian of whatever quantum mechanics is dual to JT gravity. But because we're integrating over this Hamiltonian with some weight, there's not a fixed Hamiltonian, but rather a probability distribution with a very specific type of probability distribution that has this simple kind of probability density. Okay, so that's JT. So the next step is going to be to incorporate these defects. And essentially, we're going to be able to follow the same steps. We're going to define the theory by allowing for points like this, where the metric isn't smooth, but rather has some conical defect. And we're going to include these defects with some amplitude lambda. So there are two parameters in the theory. One is telling us how strong this defect is. So there's this, which is this alpha. And the second is telling us how likely it is for a defect to be included, or rather how we should weight the defects in the sum of the path integral. So that now we're going to integrate over not just hyperbolic surfaces, but hyperbolic surfaces with these conical defects in them. So here's an example, genus 1 with 2 conical defects. And now our genus expansion becomes a 2-parameter expansion in both the genus and the number of defects. So K is labeling the number of defects, and we have this lambda to the K with this symmetry factor K factorial. And now we need to compute the partition function with fixed genus, fixed number of boundaries, and fixed number of defects.
Henry?
Yes.
Is alpha quantized here?
So alpha, we can take it to be anything we like here. Okay, it turns out that alpha has to be...
From the point of view of the reduction of the SL2Z black holes, you might anticipate that alpha is quantized,
so
but I guess you're saying... yeah, from the point of view of the 2D theory in its own right.
Theory, it's natural to pick rational alpha, if you like, yeah. or rather 1 over some integer. But from the 2-dimensional point of view, you can pick whatever you like, and there's no particular reason why those seem to be picked out.
Okay, sounds good.
Okay, good. Okay, so for JT, there was a particular special case that we had to treat on its own, which was the disk, because that we couldn't play this strategy of cutting, so we couldn't cut off this trumpet piece, and we had to treat that something separate. We've got a new example like this now, which is where you have, again, the disk, but now with a single defect. So the geometry looks like this. It's got this conical defect at the tip. And this was computed by, the amplitude here was computed by Mertens and Toriachi. And it turns out that you get this by taking the trumpet amplitude, that is with this geodesic boundary B, and you sort of analytically continue B to some imaginary 2 pi I alpha. And you can sort of understand this from SL2 representation theory. This is the B, or B is something that labels hyperbolic orbits of SL2, and alpha is labeling elliptic orbits. That's sort of naturally related by this relation in the eigenvalues. But the important takeaway here is that a defect is behaving like a geodesic boundary of imaginary length, and that's going to turn out to generalize and also work at higher genus. So again, we have this expansion in genus and in number of defects, and we can play this game where we cut along some geodesic. We have the same trumpet on the outside, and on the inside we have a Weil-Petersen volume, but now over hyperbolic surfaces with these cone points, or these conical defects. so here, if we want to do this strategy, we really need to take the conical defects to be to have a sufficient strength. So it gives us this restriction on alpha. So to be conservative, you can make that restriction on the parameters. That I suspect that things work for bigger alpha as well. Okay, so now we need to know what these Weil-Petersen volumes are with conical defects. And it turns out that you get those by taking the Weil-Petersen volumes with boundaries and playing the same game where you take those boundaries and you turn them into defects by making their lengths imaginary. And this is proven by these mathematicians to work, again, with this restriction on the parameters. And the same result was used recently in a rather different context with JT in interspace by Jordan Alex. Okay.
I think
So
actually
this is everything.
Yeah, I think actually that math proof only works when alpha is 1 over an integer, if I remember correctly. Is that right? Like, because the way that they prove it is by taking an n-fold cover. So like, yeah.
I thought it worked for continuous alpha, but I may be wrong. We can.
Okay.
I'll look it up.
Yeah, I don't remember, but my impression was that at least the Doe-Norbury proof works by taking an n-fold cover. So you can take alpha to be 1 over n and then go to a covering space where everything's smooth. But maybe there are other ways to do it that work for continuous alpha. Okay.
Yeah.
Okay.
Yeah. Okay. What's the next thing to say? Good. Okay. So we've got everything we need now because we know these Weil-Petersen volumes, and we can then glue everything together with these trumpets and get all our amplitudes. So I'm only going to talk about the most important thing for us, which is going to be the disk with some number of defects included. And to start with, we're going to make a connection to the Maloney-Witten 3D gravity calculation by doing a strategy of just looking for classical solutions and the loop corrections on top of those classical solutions. And in this case, there are actually just 2 classical solutions. One is the disk, and one is the disk with a single defect. If we have multiple defects, the action tends to be minimized when these things come together. So they want to attract one another, and there's no point where they're all stable. So we really have to do a sort of off-shell path integral if we want a higher number of defects. But these 2 guys, this is the same density of states we saw before for the disk. And this is the result you get for the disk with a single defect. And in particular, if we go to very low energies, you get this, again, distinctive to square root edge. But the defect gives you something that goes like 1 over square root of energy. So this suggests that there's a restriction on our parameter lambda. So if lambda is negative, it looks like at very low energies, we get a negative density of states. And this is very closely analogous to the negative density appearing in this Maloney-Witten-Keller partition function. But now we see no obvious reason that we should stop at 1 defect. We can include multiple defects and just do the path integral in JT. And then we get a 3rd term, and near the edge, this 3rd term, it shows lambda squared because it's got 2 defects, but it looks more singular at low energies. So the higher defects seem to be saving us by just making this expansion divergent for small energies, and we just can't trust this small lambda approximation. Fortunately, we can actually do better in JT gravity, and we can see what all these corrections look like and add them up. So there's a simple formula that is not too difficult to prove for these for the Weil-Petersen volumes, where you have 1 boundary with very large length, which is the relevant thing at low temperature. And it turns out that these guys all sum, these just become a binomial series. So they become this square root of e plus 2 lambda. In particular, this is supported for energies bigger than minus 2 lambda. So what it's done is kept this distinctive square root edge, but it's just shifted where it is. So the threshold has moved this minus 2 lambda. And this turns out not to be true just to leading order at low temperature, but to higher orders as well. And you can compute this thing to your heart's content. There's a shift in the threshold, and this involves a really sort of tight conspiracy in these Weil-Petersen volumes. So there's some large number of coefficients in the, there's k-1 coefficients when you have k defects that in these, so these volumes turn out to be polynomials. And if you want this feature to be true, that it looks like a shift of the threshold, then it uniquely fixes all but 2 of these coefficients at each order in terms of what came before. So it's very tightly constraining condition. Okay, and this is the interpretation of what's going to happen in 3D gravity as well. It's going to be these extra pieces. I'm not going to say any more about what happens in more detail. I'll refer you to the strings talk and the paper, but let me just summarize the rest of those results. So at genus 0, it turns out that you can compute the sum over these Weil-Petersen volumes, the sum over any number of defects exactly. So that's true for the disk with any number of defects, but also things like this, where we have this sort of double trumpet, the two boundary path integral with any number of defects. Mertens and Turiachi are using some of the sort of minimal string methods from the early 90s, wrote down a closed form for Weil-Petersen volumes at genus 0, and you can just do this sum. And this in particular gives you an exact expression for this disk density of states. And this is the thing that determines everything else in the matrix integral. This is the sort of defining data of the matrix integral. And then you can start checking that everything matches what you expect of a matrix integral. First of all, very explicitly at genus 0, but then at higher genus, there's actually, it turns out there's this theorem of Eynard-Norrentin that tells you how topological recursion behaves under deformations of row disk, if you like. And it turns out these defects, there are very special sort of deformations that preserve topological recursion, and inclusion of defects is an example of one of the deformations that they study. We put up a new version of the paper that sort of explains this in detail a week or so ago. So I'll refer you to that. So the conclusion is that with these defects, we get the same conclusion of Seidschenker and Stanford, and we have this duality between gravity and a matrix integral. Good. So the last thing I'll say, maybe I won't bother saying this. Okay, I'll just briefly say it in words. There's another way of thinking about this, which is of the dilaton potential. This is the perspective that Witten took in his paper a little bit more. To understand this in detail, you have to, okay, it's a little bit more subtle, but there's a suggestion of a very large family of dilaton gravity theories that have matrix integral duals. So that's potentially got lots of interesting applications. Okay, so here's the summary of what we've done with JT. So in the last 15 or 20 minutes, I guess I'll talk about the Bootstrap, but it's a good time to pause for questions if there are any. Okay, good. So if you saw my strings talk, this is roughly where you can wake up, because I'll say something new. So the first thing is to say how we should uplift these two-dimensional results back to the three-dimensional context, which sort of motivated them. So the suggestion is that we had this density of states coming from the BTZ black hole. We had this other term coming from the SL2Z black holes. The suggestion is there are other corrections that resum these into this shift of the threshold. And it is going to be some non-perturbative shift that depends on the sign of the spin. And it's going to be non-perturbatively small. So this parameter lambda is going to be some exponentially small parameter here. And these, the two-dimensional configurations we needed to include were these multiple KK instantons, these multiple defects. So when you uplift those to 3 dimensions, they turn out to be smooth 3D manifolds called Seifert manifolds. And these have been studied a bit in Chern-Simons theory and various other contexts. So the proposal is you should include these guys in the path integral. There's no classical solutions for a Seifert manifold, apart from these SL2Z black holes. But the suggestion is that if you perform an off-shell path integral over these topologies, then you'll return consistency to the theory without changing the dynamics.
Henry?
So that's the proposal. Yeah.
These formulas are meant to be valid in the near extremal, but still large spin regime. Is that correct?
Yes. So, to be most conservative, you should take a very large spin and then go very close to this threshold. For pure gravity, they should also apply actually for finite spin as well.
What's the argument for that?
So the thing that controls the corrections to the topology is basically this S0, which is the Cardi entropy. And it turns out that even for spin 1, the Cardi entropy is still parametrically large. It goes like the square root of the central charge. So this two-dimensional theory is parametrically well controlled in terms of these topological corrections for any spin, but at large central charge. The only thing we don't have strict control over is, at the moment, we don't properly understand the one-loop corrections from graviton KK modes. But I think that's a technical hurdle, and I don't think they're going to be particularly.
So you're saying in finite spin, you expect this to still hold, and the central charge is much larger than the spin in that situation. So is that correct? That's what you're talking about.
Yeah. So it depends on how the most conservative regime is very large spin much bigger than central charge, and then this should actually be pretty universal. If you want to be less conservative, then you can take central charge of the same order as spin, which means that the black hole has horizon size of order ADS scale. In that case, we'd expect semi-classical gravity should work. If you want to be less conservative still, then you can take the spin to be order 1. And I think
in that third least conservative regime, you're still claiming that you think this should hold, but there's no derivation. Is that correct?
I think so, but we don't. We don't really know what's going on with these KK modes, so it involves a bit of abstraction.
But still, there it's important that C is large, of course.
C has to be large, yes. So really, the thing that's
you need X not to provide. Yeah, exactly. Yeah.
So that's the product. It's square root of C times J, essentially. But yeah, so I mean, the reason I'm calling this a proposal in 3D rather than a complete solution is that I don't actually know how to compute the path integral on Seifert manifolds and sum them up and all the rest of it. And this is I think is strongly suggestive that this should work, but there are of course important details to work out. So the last thing to go through is get onto the Bootstrap pieces here. So I don't know how much of this I'm going to get through. So let's just summarize the general structure of the argument. So we're going to look at a large spin expansion of the density of states. So that means you fix h bar and take h to infinity. And from this, we can get asymptotic formulas for the density of states. So this is essentially the Cardi formula, or a large spin version of the Cardi formula that applies. So here we're fixing h bar to be very small. So it's all close to C minus 1 over 24. But we can also consider the density of states weighted by -1 to the spin. So the even spins minus the odd spins. And there's a different sort of Cardi formula for this. So the first thing to do is to actually describe a rigorous sense in which these asymptotic formulas hold. So these twiddles here are so far sort of suggestive but not rigorously meaningful. We're going to make them give a rigorous statement that means that once we, roughly speaking, if we take some smeared version of these density of states, then these formulas are correct. As Nathan commented on earlier, this thing comes from just the modular S transform, as is familiar, and the second one comes from some different modular transform. So the possible problem here is if the second guy is bigger than the first guy, because the first guy should be positive and the second guy should be the same elements but potentially with signs, so it should be smaller than the first. And it looks like we might have a problem with very small h bar. There's not immediately a sort of rigorous tension because we're working at some fixed h bar and h to infinity. And to get to this problematic regime, you have to take a combined limit of large h and small h bar. H bar in particular is exponentially small. So it's really important to look at this combined limit. And it's kind of hard to look at that combined double limit to zoom in on this regime with a negativity, but we can get some suggestions for what goes on by just looking for what the correction terms are to this density. So the idea is that there's some correction term here that beats that is larger than this leading term in the density with signs. So the solution suggested by Nathan and friends was that you should add another term that looks like this. So it's got this 1 over square root density to rival this density, but it comes with some exponential growth with a coefficient that's at least as big as a half. And this is the sort of thing you'd get from taking some light sort of matter state or some extra state with dimension less than c over 32, which is well below the black hole threshold, and you take the modular S transform. So the only thing I'm going to say is that in the end there's another possibility here, and this is what's suggested by this shift of the threshold, is something that grows more slowly with spin with H, but is more singular with H bar. And this is the sort of thing, if you take the S transform, to get this, you don't need any light matter, rather you need some number of black holes, sort of near the black hole threshold, but not just finitely many, but infinitely many. But it's only infinitely many in a very mild way. There's roughly 1 new state per spin. And this is, so this is the alternative, is that we need to augment the Cardy formula by just some extra polynomial term in the density of states. So this is an exponentially small correction to the entropy. So it's pretty mild, but this is good enough. So you don't need new matter. I've got to strategize on how I'm going to go through this. Well, we'll see how far we get. Okay, so the way this, to start the argument, I'm going to just introduce some notation that's hopefully going to be familiar. It's just a new parameterization for the conformal dimensions. So we start at this c minus 1 over 24 is interpreted as the BTZ threshold, and add this quadratic term in P. So we're going to use P and P bar instead of H and H bar. We'll just note 2 features here. One is that there's a symmetry under P goes to minus P. So we're just going to choose to make everything symmetric under that. So we don't have to worry about it. And the other thing to note is that when you have dimensions below the BTZ threshold, this corresponds to imaginary values of P. So we have to bear that in mind. Okay, so in that language, we can write the partition function, which is just the usual trace over the Hilbert space, as an integral over the characters, which, the characters of the theory, times some density of states in terms of these P and P bars. And we're including these factors of 2, so we don't overcount from this symmetry. And this rho is the density of primary states, so it's basically a sum over delta functions. And we're symmetrizing under this P goes to minus P symmetry. But it's, if we have a Virasoro primary with dimension corresponding to pk, then we just include these delta functions, where chi's here are the Virasoro characters, and they're these guys which are Gaussians in P with some tau dependence that summarizes the descendants of the theory. And the vacuum is a little different because it's got a null descendant, so you have to subtract some states. Okay, so that's just the notation. So now let's, the idea is to talk about modular invariance, not in terms of the partition function directly, but rather as a statement about the density of states itself. So we don't have to talk about the partition function. It's like, so if we have so just for this, this little bit, I'm going to suppress the dependence on the barred variables and just keep the dependence on the unbarred variables. We have our expression for a partition function in terms of this density of states rho. Then if we take a modular transform, that is, you take tau goes to minus 1 over tau, then this is some different function, and this will have a different expansion in terms of some some density of states, S rho, and that density of states is going to depend in some linear way on the density of states we started with. So Z could be essentially any function here so far. The way we get S rho is going to be by integrating against some kernel like this. And if you sort of plug this in and strip off the characters and so forth, you learn that this kernel should be something that relates the characters to the modular transform characters. And the characters, as we said before, are Gaussians in P. And when tau goes to -1/tau, you're taking a Gaussian to an inverse width Gaussian. And there's some integral transform that does that. And that's actually just the familiar Fourier transform. It turns out that the statement in particular, a statement of modular invariance, that the partition function is invariant under tau goes to -1/tau, is equivalent to a statement that this rho is invariant under a Fourier transform in both P and P bar. So I'm surprised that I haven't had any whales of objection so far, that I've been including these delta functions of P where P is imaginary. I should briefly put in this slide, which explains why that makes sense. So this rho is some funny type of distribution. So it includes these delta functions for imaginary P, and it's got some exponential growth. So it's not it's not a Schwartz distribution or a temper distribution or one of these things that you're going to look up in the usual in your mathematics books. It's something that it lives in some larger space of distributions that are called D primed, which is the dual space to some smaller space of test functions. And if we want delta functions at imaginary P, that means that we need our test functions to be entire analytic. And that means we can evaluate them at imaginary values of P. And the only important example for us, we need to be able to integrate our density of states against characters. And the characters have these properties of their entire functions of P. So if you're, so these test functions, you should think of Gaussians. And then the density, the density of states, which is the distribution, is really defined by its pairing. This is the usual mathematical formalism that sort of underlies theory of distributions. Okay, so that'll be important, but most of the time we can just sort of follow our nose and be and treat things as you naturally would, and you won't go too far wrong. I didn't for time. Not very well. Okay.
So don't.
So maybe the one thing I say is how.
So I mean, you can take a few extra. You can take a few extra minutes. You don't have to rush.
Okay. Thanks, Leonardo. Great. Okay. Okay. So once we've got this way of thinking about modular invariance in terms of the density of states, we want to get some asymptotic formulas from these. So we want to get some kind of Carli formula. And so we're interested in our density of states. Again, I'm for now just suppressing the right moving dependence. We want to look at what happens to this at large P. So to do that, we write it in terms of its S transform variable. So it's a Fourier transform of the S transform density of states. And modular invariance tells us that S rho is equal to rho. Now the important thing for this large P expansion is this kernel, and in particular, when P primed is imaginary, this is growing exponentially with P. And the rate of growth depends on how large the imaginary part of P primed is. So if we want to expand the left-hand side at large P, we need to pick out the pieces of the S transform density that have the support on the largest imaginary part of P prime. So that just corresponds to the smallest twist. So this is saying in fancy language, unfamiliar language, things that you know very well, which is that if you want to know the high energy density of states, you should look at the S transform of the ground state. And then corrections are organized by the lightest states. So that tells us that because the lightest state, the one with the largest imaginary part of P primed, is the vacuum, it tells us that there should be a sense in which the density of states is dominated by the S transform of the vacuum density of states. And there's this cinch formula that people might recognize. And this is if you look at this near extremal regime that we're interested in of large p and small p bar, then it looks like this. So this piece is the Cardi formula. P is roughly the square root of spin. And once you sort of include Jacobian factors and so forth, this corresponds to this square root of h bar edge, square root of energy edge. Okay, so what we'd like to do is make these twiddles more precise. And the way I want to do that is by looking at some test functions. So we're talking about these things as distributions. So we need to, if we want to make this rigorous, we need to say something that makes sense for these sorts of distributions, which means we should talk about integrating against one of these test functions in this space. So what we're going to do is choose some window function, think of a Gaussian or something, and we're going to integrate that test function against the density of states, and then we're going to move it to larger p and integrate it against the density of states, move it to larger p, and then we'll see how that behaves as we move this sort of window function. So we're going to look at the pairing of the density of states with some translated test function. So TP here means you just shift the middle of this test function. And what we're going to say is that rho is of order some function f in this space of distributions if that's true when you integrate it against test functions. So this gives us a rigorous way of saying when a distribution is smaller than some function in a particular sense. And I'll compare this to some other ideas in a moment, but first we'll just say how easy it is to use modular transforms to get results like this. If we want to talk about bounding some S transform, that's a Fourier transform, that's defined by moving the Fourier transform from the density onto the test function. But the Fourier transform of a translated test function is just this exponential phase times the Fourier transform of the test function. And you can easily bound this right-hand side. So it's sort of easy to, I won't go into the details, but it's relatively easy to start saying rigorous things using modular invariance. So in particular, there's this version of large spin Cardi, which says that the density of states is the S transform of the vacuum plus some piece that decays at a rate that's determined by the lightest non-vacuum primary. Yeah, in this particular sense, that if we integrate the density of states against some test function, we get something that's bounded by this. A few features of this is that because we're fixing this test function psi and then translating it, we're not translating the test function and making it narrower at the same time. We're fixing the width in p. When we go back to the usual variables of spin or dimension, the width is actually growing with the square root of dimension, the square root of spin. So what it's doing physically is smoothing out fluctuations which happen on scales much smaller than the square root of spin. So in particular, things like differences between odd spins and even spins are going to get washed out in these sorts of asymptotic formulas. It's both a feature and a bug. It means you can make stronger statements, but you can prove things that are rigorous, but the statements you get are perhaps weaker, for example, than those you get from Tauberian type theorems. But on the other hand, it's really easy to incorporate higher order corrections, and you can. So it's sort of a complementary approach to these Tauberian type results, and it's simple to apply when your distributions aren't necessarily positive and so forth. Okay, these are a few features of what these formulas mean. Okay, I better wrap up soon. So let's just say, okay, I think I'm on the last couple of slides. So, to say something about this possible negative density of states, we need to use other SL2Z transforms, in particular this ST squared S transform. And it turns out that there's a generalization of this modular S transform being a Fourier transform to any one of these guys. So in particular, it's generated by S and T. So T is what you get by taking tau to tau plus 1, and it gives you this factor, which is basically -1 to the spin, acts diagonally. And there's a representation of the modular group generated by these two guys. So in particular, S squared equals 1 is just the Fourier inversion theorem, and then there's a slightly more involved thing for this relation. But for us, the only one that's going to be important is this relation. And this is what follows from the st² transform. So you give these phases -1 to the spin, you take a Fourier transform, noting that there's a 2 here where there is not a 2 here. And this gives you, again, something, density of states modulated by spin. And we can use this, this statement of st² invariance to get an asymptotic formula for the density of states with a -1 to the spin. And it looks similar to before, except this Cardi density is half of what it was, the exponential is half what it was before, and we also don't have this, this p-bar squared factor. And this corresponds precisely to this 1 over square root of h bar, 1 over square root of energy edge. Okay, so the first statement here is that we've these rigorous results really apply at fixed p-bar, so we don't immediately have a sharp contradiction. And if you try to take a simultaneous limit where you take p-bar to 0 and p to infinity at the same time, then it's really hard to bound what the corrections look like, and it's very hard to make any rigorous results. But we can do something suggestive by just looking at what the corrections look like in this. Just take this, the fixed p-bar, p goes to infinity limit, and ask what the higher order corrections look like, and are those higher order corrections the sort of thing that would resolve this tension? And the short answer is that yes, they are. So in particular, this proposal of the shift of the spectrum gives you corrections to the density of states that go like 1 over p-bar squared with some factor that's independent of p. And this correction is coming from something in the S-dual channel. So these corrections are dominated by the lowest twist in the S-dual channel. Because it's independent of p, these come from things at dimension of order the BTZ threshold, which is what this delta p is telling you. But because it's singular in p-bar, it's got this funny singularity. When you take the Fourier transform, you get something that actually grows polynomially with p-bar, which means there's a density that is growing polynomially with spin. So this turns out to just be an order 1 density as a function of spin in terms of the spin variables. The conclusion is that if your density of states didn't include any new states below the black hole threshold, but included just polynomially many extra states at the BTZ threshold, when you take the modular transform, you get terms that look like this. And if you want the higher order corrections, then you just have to include more terms that are polynomials in spin. So this is a pretty mild sort of enhancement of the number of black hole states. And the thing that sort of inspired this whole thing was something very similar that happens where you take the modular transform of families of multi-twist operators, and the same phenomenon that these resum into some shift of the BTZ threshold. But I won't say any more about that unless people ask. Okay, so this is the summary. We have a density of states that in this rigorous smeared sense is dominant, it has a large P expansion given by the lightest stuff in the S transform. We also have this density of states modulated by this -1 to the spin, and that's dominated by the lightest stuff in the st² S transform. There's a rigorous statement of what these things mean. And we can compare these and look at what the corrections are, and we can make everything consistent by including just these polynomially many extra black hole states. At this point, there's now a load of speculation you can make about what 3D gravity should be, which doesn't really have a great deal of evidence, but it's fun to speculate. But maybe I'll instead stop and invite any questions or comments. And thank you for your attention.
Thank you very much. Questions?
Hi, Henry. In 2D JT case, can one put defect on the boundary of disk instead of the bulk?
So in principle, we're sort of integrating over the location of the defects to be anywhere. But it's but when you move them close to the boundary, that contribution is essentially exponentially suppressed. So this, from the dilaton point of view, the boundary is a very large value of the dilaton, and the amplitude for including a defect goes like the e to the minus dilaton. So they basically, you can ignore them. And after you integrate out the dilaton, the geometry sort of restricts you to, it's a bit like the deviations in the Schwarzian mode that mean that for some reason this boundary is wiggling right into the middle of ADS. So it's just something that's in principle there, but in practice is not relevant.
So like in Liouville theory, Liouville gravity case, one can put like vertex operator on the boundary or in the bulk. In the bulk corresponds to the putting defect in the bulk. On the boundary, it has a different correlation function, right? It's not just the limit.
Sure. Okay. You want to put a defect? I haven't. Yeah. You want to impose that a defect has to be at the boundary. Yeah. I haven't thought about that, so I'm not sure I can say anything intelligent.
Thank you.
I'd have to think about that.
Henry, I think for like any SL2Z element, you could probably cook up a universal formula where for the, some combination of the density of states that depends sensitively on the number theoretic properties of the spin. Do you see those being good for anything, or?
Good for anything. Yeah, so I was concentrating on just this ST2S guy, but of course there are versions of this where this is any phase is e to the 2 pi I p over q for any rational.
And the vacuum will dominate.
So you get an asymptotic formula where the coefficient here is 2 pi divided by the denominator in this phase. Whether they're important or for anything, I don't know. I mean, so this -1 to the spin, guys, seems to be important because it's giving us this extra 1 over square root. So it's got to get potentially getting us into trouble. But the higher spin versions are not any worse.
They're not qualitatively different in that sense. Yeah.
So I don't immediately have any sort of obvious application. But
are there any negative terms coming from those higher ones?
Yes.
They come with phases.
There are. They depend on. So like if you include like ST cubed, I guess it is, then you get. Okay, I'm not sure which one it is, but you get something that depends on like the cosine of 2 pi times.
Like all of the terms other than the first one will give negativity. It's just the s equals 2 is the most severe one. It'll give negativity because for various values of spin, mod, mod 3, mod 4, etc.
What I mean is, have the defects that you've included in the JT language, have they removed all of the non-unitarity, or is there now a subleading non-unitarity that's still there?
So you can just include multiple. It's straightforward to do this JT analysis with multiple species of defects. So you can just include, if there should be a family of defects labeled by rational numbers between 0 and 1. So I've been discussing the rational number equals a half defect, but you can then go and include these families of more exotic ones. And then once you, again, sum over those defects, if you included 1, again, I guess you could have a problem, but once you sum over them, everything is fine. One interesting thing is that from the matrix model, I don't know if it has something similar in the 3D case, is that the place where the higher spin versions, or rather these more complicated phases, the place where they become important is also the same place where the higher genus on the disk becomes important in JT. So they're with where you're zooming into this Airy regime, if you know about, where you're starting to see discreteness of the spectrum. So that shift from the shift from the higher terms apart from these two, the other shifts are of the same order as the discrete, the gap between states at the edge, turns out.
Henry, I didn't totally pick up the answer to Tom's question. There is some residual non-unitarity, and you gave a description for how you could fix that, or there isn't?
So I think if you were to just include one of these defects, just the SL2Z black hole on its own, then again you get negativity, but the same solution works. Same solution where you sum over these defects applies for any number of defects. Okay, there's again a question of whether it converges when you sum over infinitely species, which I don't know about, but
species of defect are also labeled by SL2Z mod Z cosets, right?
they're labeled by rational numbers between 0 and 1, it turns out. They're labeled by members of the double coset.
Which is the, okay, good.
Which is not quite the same thing that labels the topologies.
No, it's a coset, it's a quotient of that by Z, yeah. Actually, can I ask a question about something you said? So like on this slide, for example, you're emphasizing that you need rigorous smeared asymptotic formulas. I would have thought that a smeared asymptotic formula is only useful if you're in a regime where the discreteness of the spectrum is important. And usually in a chaotic theory, you would think that everything's exponentially closely spaced. And so there's not really much utility to working with a smeared asymptotic formula instead of a just kind of naive one. Are you saying that you're in a regime where the discreteness is important and that's why you need to work with the smeared ones?
Smearing here is really smearing over spins, which are really integers.
Sorry, I didn't hear that.
The important thing, the important smearing that's going on here is not the smearing over energies so much. Yeah. It's the smearing over spins.
I see.
Where there's very little integer spacing. And it's just the thing that wants to wash out.
I see. That's the smearing that's playing the important role for you. Okay.
That's the thing that's physically important. But the other thing to say is that if we want to say something sort of rigorous and universal, as you well know, then we have to deal with the fact that lots of CFTs are not chaotic. And whatever we say, a million free bosons does for trees.
And then you're in Tauberian land or something like that.
Your results are going to be weaker than what you'd expect for chaotic.
Right.
But if you want to assume a twist gap anyway, it's not that big a deal.
But as if we want to assume a twist gap, then presumably that means the theory is chaotic, but we don't really know how to put that information in. So it's a new idea.
Henry, can I ask a question about your formula for the shift? For the shift, you had a formula where you had something like square root of e minus j plus this shift, which was like -1 to the j e to the minus root j or something.
Let's see. Let's see. Maybe here. This one.
Yeah. Perfect. You said you need large. You'll trust this at large spin. As a function of the twist, do you expect this formula to take this form only near the DTZ threshold, or some finite distance away as well? It'll take this exact form.
Oh, with the square root?
With the square and also with the same shift in particular.
Well, so the shift is defined as this edge. So that is locating the edge. And then this square root is something that would only apply very close. In fact, like exponentially close to the edge. So there's actually some modified density. So for the, I don't have the slides here, but we have, for the JT case, we have some exact formula that involves our integral of Bessel functions for what the full density of states looks like. And it shifts the edge, but it doesn't just shift the whole spectrum rigidly, it shifts the edge and then sort of changes the shape in between.
This is the analog of sinh root E, but with defects. Is that right?
Yeah, so there's you get sinh root E plus the thing that it's an exponentially small modification at large energies. It's much smaller than a modification you get from a rigid shift of the whole density. And it's got some sort of more detailed form that you the JT result can't can't be precisely true in 3D gravity once you go very far from the edge.
But you might expect it to hold at all orders perturbatively near the edge, perturbatively in the twist.
You might hope that if you zoom in on this regime where you take a simultaneous large spin, small twist, then it should be good. And an interesting question is to take that more detailed formula that we've written down for the density of states and ask what that tells you when you do the modular transform. And at the moment, I don't know what the answer is.
Thank you.
So
yeah,
going back
just get away with.
Sorry, going back to your final slide and to the big picture. So you have a proposal to cure this negativity by summing over additional topologies in pure gravity, if I understand correctly. Of course, you're still going to get something continuous, presumably. We don't know.
Well, there are several things that can happen. In principle, it could magically turn out that you get something discrete. You know, such things happen for BPS state counting and so forth, where you really get integer degeneracies and all the rest of it. But that sounds like it would involve a massive conspiracy. But at least if you have a continuous spectrum, then perhaps that's not as bad as we might have thought.
About to expect what you were going to tell me next is that continuous is okay because we're going to interpret this as an ensemble of theories.
Yes. So yeah. So the basic point here is that the sort of topologies we've included, if we're going to include these Seifert manifolds, then there are just as good topologies that connect multiple boundaries. And this is an old problem in ADS-CFT, is how you should interpret those. And because the partition function on a disconnected manifold should be the product of partition functions on the components. And the wormholes seem to spoil that. So there are two possibilities. One is that there's a conspiracy that means that despite the fact you've got these connected things, nonetheless, the result is a product once you do the full sum, which is a massive conspiracy, or there's something connected. And in the latter case, there's a natural interpretation in terms of this ensemble. And in the former case, if there's a conspiracy for the factorization, then perhaps there's a conspiracy to remove the quantity as well. But in the end, there's a zoo of topologies. We don't really know how to sum over them. That sum is divergent. It's really extrapolating to say anything from just including.
Is there any way to this? So there are this other proposal by people who are attending where you instead include some sort of orbifolds, which are like additional light matter. Could both proposals be correct for different ensembles, or is there a way to decide which one is correct, or how do we proceed from here?
Yeah, so both could be, yeah, they're different theories in the end, I think is the answer. So the other,
in both cases, low energy observers still just see boundary gravitons though.
It looks, yeah, so low energy, they look the same, and then
one qualitative difference is what the twist gap is. So for ours, the twist gap is on the order of C over 32, and for Henry's, it's C over 24. I think one way to answer this question definitively would be if from some numerical bootstrap or something. So this problem is a little bit subtle, so we can discuss it. But roughly speaking, if from numerics or analytics, you could prove either that you can construct a modular invariant function that's positive everywhere with a twist gap of C over 24, or you cannot. If you just from CFT arguments can prove one way or another, I think that would be I don't know if you guys agree.
Yeah. So my perspective on it would be that that if you follow Nathan and Scott and Alex's proposal, then I think you should still include the Seifert manifolds or larger numbers of defects and so forth, and actually everything would result in just this shift of the edge in the end. So it's just a different theory with some extra dynamics that solves everything in a more straightforward way. But so I didn't emphasize the So if you take this canonical defect proposal, for example, the density of states near the edge goes like 1 over square root of energy, which is, okay, that's fine. There's nothing immediately wrong with it, but without some good reason for that to be there, it's a strange thing. It's not what you get in generic Hamiltonians and so forth. It's something you'd get in a supersymmetric Hamiltonian. So my question is whether the proposal of Nathan and co has some more natural home in a supersymmetric theory, where this 1 over square root energy density is more natural. But this square root energy is just the generic thing you expect from chaotic Hamiltonians, so, and random matrices and so forth. So I think that should still be there in the Benjamin Collier-Maloney model once you include off-shell topologies plus the conical defects.
I don't see why they couldn't both be describing legitimate theories, especially if you allow that one theory could be continuous and the other one discrete. You know, for example, addressing Nathan's question, it's a logical possibility that you could have a large gap if you allow the spectrum to be continuous, but not if you don't.
Yeah, I mean, I think maybe something that was, maybe this is what Henry, you were trying to say. It's like, is your suggestion that the proposal where one includes orbifold states is not a generic chaotic theory, but could even be an integrable theory because it doesn't exhibit the square root edge?
I think it's more just that JT supergravity has this 1 over square root.
Oh, I see what you're saying. That's what's
yeah, or any, well, let's see.
I see. No, that's clear.
I mean, for example.
I mean, can I?
There's an option of once you have your model with orbifolds, with these with this extra dynamics, there's then a question of whether you want to include off-shell topologies as well. So
right.
There are 2 separate choices. I've been suggesting we should include path integrals over off-shell configurations. You suggested we should augment the dynamics. I mean, there's then 4 options. We can do neither. We've got a problem. We can do one, or we can do both. And
there's 4
my
logical
suggestion is that your model is nice, but I think the more natural thing is to do both.
Can I ask,
and the off-shell.
Can I ask a different question about off-shell topologies? So there's a different way of thinking about 3D gravity, which would just be in Lorentzian signature, where you just think about it as a surface times time. And then you can actually look, you know, solve the constraint equations. And in this language, 3D gravity just basically looks like dynamics on the cotangent bundle of Teichmuller space or of moduli space. And a BTZ black hole just looks like a cylinder times time. And so you might try and investigate off-shell topologies by adding handles to that cylinder. And I think I think those look like Seifert manifolds if you reduce them. Well, I think that if you continue to Euclidean signature, you could interpret them as Seifert manifolds. And so one natural thing that I think is you're suggesting is that if I were to quantize the cotangent bundle of moduli space of like some general Riemann surface that, you know, looks like a black hole out here, but has some fancier topology, that would lead to little wiggles in the formula for the energy as a function of, or for the threshold as a function of spin. So that could be like that's like a totally different way of proceeding, but it's kind of a much more boneheaded, you know, here's a phase space, here's a Hamiltonian, let's quantize it. But again, it's like one of the things that's confusing is what you in your paper with Don pointed out, which is that once you start playing that game, there's vast numbers of null states you need to worry about. I don't know, have you thought about that or no?
No, we should talk. Doesn't sound boneheaded. That sounds stupid to me.
Or are we talking right now?
Yeah, so maybe you should talk more. If there are no other questions, we can thank Henry and all the participants for this beautiful talk and lively discussion.
All right.
And bye-bye, everybody. Thank you.
Thanks for all the questions.
Sorry, somebody has a question?
I was thanking everyone for all their input and No matter.
Okay, thank you.
Right.
And